Okay. We should have most of the, there's a couple of the exams that aren't graded yet. They're the ones that like maybe an online student took or whatever. So, but most of all, most everybody has taken the exam. And so the average was like a 66.7 or something like that. It's slightly lower than what, average should be in the 70 somethings. So a little bit lower, but this class is set up in a way that first of all, you can totally retake exam 1 or exam 2, so and a different version, so the same type of problems but different problems. It's not just the same problems with different numbers, it's another set of problems, so you can totally retake it, but the exam is, the whole course is set up in a way that you actually could go in and make about a letter grade higher than your exam grade average if you do all the homework and you do the trust project and all that kind of stuff. So you should be okay no matter what grade you made because of the retake, but if you're feeling not so great about it, then you do have other chances to make it up. But grades should be there. You can come before class sometime. My office hours are before this class, so from 8-ish to 10-ish or so on Monday, Wednesday, and Thursday. And if you want to look at your actual exam and see things you might have missed or whatever, so you can do that. We're moving into exam 2 material. We actually started exam 2 material last time with the frames and machines, or maybe 2 times ago now. And so we're going to continue that in the idea of beams. So we're still kind of talking about frames and machines, but we're specifically talking about this idea of beams. So we're under frames and machines. But we're specifically talking about this idea of beams. And we made the distinction a couple of classes ago that frames and trusses are not the same thing. So frames and trusses are not the same, but they have some of the same elements. They have like pins and they have members and that sort of thing. The difference between the two of them is that trusses only have 2 force members, or 0 force members, but that's okay. Those assumptions that we made set it up so that trusses only had 2 force members. Wow, if I could write, that would help. But frames, the way that they could be loaded, specifically that they could have member forces directly applied to the members, or external forces directly applied to the members, frames, they have at least one what we're going to call beam. And the 2 force members, they only had axial forces. So they could be in tension or compression, but it was an axial force. So either stretching them out or compressing them. We're still not worried about compressing them and they buckle. We'll talk about that a little bit later in the course, not later today, but later sometime. But a beam, it has some kind of flexural force. We'll call it that. We'll actually use another word a lot called bending moment. That may not make as much sense just yet, though. But the same idea, where you've got a force that's not applied axially, it's got some kind of tendency to want to flex or bend the beam. So, for instance, you might have a beam, and this beam might be a beam by itself, or it might be a beam that's in a frame or a machine, and it would still work similar. So this one, remember when we had a pin at one end, well, a pin somewhere and a roller somewhere. They don't necessarily have to be at the very ends of the beam, but when we had a pin and a roller, we called that simply supported. And we put some kind of force, that's going to make the beam want to bend. So it's going to, this is exaggerated, but it's going to want to bend downward somehow. That's the flexural, the bending that we're talking about, where it's not stretching it out or compressing it. It's actually doing both. It's actually stretching and compressing it at the same time, and that's a different thing. So what if we looked at a bigger picture of this thing, you know, take maybe a little section and blow it up into a big piece, exaggerated so that it's not, you know, it's got a lot of extra bend into this little piece. But once you exaggerate that little piece, now it looks like you could be able to see that this bottom line I drew is way longer than the top line. It's not an optical illusion. You know, sometimes you get these and they're optical illusions. That one really is longer. It really has stretched out on the bottom. So somewhere down here at the bottom, it has stretched, and there's some maximum tensile. I wrote it as a stress here, but also strain. You know, you've stretched it very much. Whereas the top part, somewhere, there's, do I want to draw it that way? That's not how I want to draw it. Well, we can draw it that way and put a zero line. And this will be sigma max compression. And we'll make the line, you know, this is 0 right through the middle here where there's no stress. So this is a negative number, and this is a positive number. And there's some, you know, profile that's more or less linear where it goes closer and closer to 0 in the middle somewhere. And then the further away I get from that middle point, it gets more and more on the top side compression and on the bottom side tensile. And this middle point is interesting because if the tension is a positive number and the compression is a negative number, these are stress numbers, then to get from +1 to -1 or whatever they are, somewhere I had to go to 0. And this point, let's make it green. This point, you know, there's some line through here where the stress is actually 0. Sigma equals 0 psi or whatever your units are. And so that point is interesting. We actually call that dotted line the neutral axis. Neutral because there's not positive or negative stress there. So that's an important part of the beam because it's the transition between the compressive stresses on one side of it and the tensile stresses on the other side. Compression's not always on the top. You could have a beam that's bending the other way where tension is on the top. Most of the time, beams are not loaded that way where they bow up in the middle, but they could be. Or there could be some part of the beam that bows that direction, maybe like on a diving board where there's part of it that's hanging over the edge that's unsupported. It would have tension on the top and compression on the bottom. But there would still be some point between the two of them where there's no stress. And we called that the neutral axis. And the thing about it is, let's just say that this beam was a rectangle. You know, this is the side view. Remember, these are side views here, just to be super clear about that. And a cross section, if this beam is just a rectangle, would be a rectangle. You know, the cross-sectional area would be something like this. So this is cross-section. We'll call it cross-section AA. Sometimes on a diagram like this, you might see a symbol that looks like this. And that's showing you that, hey, somewhere there's going to be a little diagram. I've got it labeled at the top at A and the bottom as A, or it could be BB or whatever. It doesn't matter what the letters are. But I've said that this little symbol is basically chopping this side view in half, and somewhere on the diagram there's a cross section that matches those two letters, and it shows you what the cross section looks like you're looking down the length of the beam. So in this case it's a rectangle, or maybe it's an I-beam or a T-beam or whatever shape beam it is. The neutral axis, when you look at the cross section, is at that centroid. So the centroid that we did a week ago or whenever, you know, for a rectangle, the centroid is just right in the center of it. And that neutral axis goes through that centroid. So that NA is neutral axis. So that's usually an important thing because it's the transition between positive and negative stresses, tensile and compressive stresses. And there's a lot of things that equations that might revolve around that. For one thing, if I know where the neutral axis is and this stress profile is linear, like I've drawn it here, it's a straight line, then I can figure out how much stress there is if I know information at certain points. We'll get into the stress calculations maybe later in this lecture a little bit. Mainly right now we're just going to talk about the beam bending and everything, and not so much on the amount of stress that's going on. But anyway, this neutral axis is an important thing. And this is very different from a two-force member that is, the whole thing is either tensile, so it's stretching, or the whole thing is compressive, it's compressing, getting shorter. Beams in flex, bending, whatever you want to call it, they experience both tension and compression at the same time. And so that's different. And so that's why they're going to have different ways to deal with them than trusses do. So you do have to be able to tell the difference between trusses and frames. And the biggest giveaway usually is that a frame is going to have one piece at least. It could have a whole bunch of pieces, but at least one piece where there's a force that's not at one of the supports, or not at a pin or something like that. It's on the bar itself. And that's going to give it away that that piece is a beam, and therefore you have to treat this whole structure like a frame or a machine. And you can't treat it like a truss where you can do method of joints and method of sections. So let's do a simple one. This is really back to just frames, but a relatively simple one. And let's say that we've got a member that goes out kind of horizontal, or exactly horizontal, and one that goes vertical. And then there's a little connecting piece between them. And we're pinned down here. Over here, there's going to be a roller on some kind of little ledge. We'll have a force right here. So this force, well, we had already made it a frame when we made members that had more than 2 pins on them. So we made pieces that had 2 pins and a roller. There is one piece in there that so far looks like a 2-force member. That would be a piece of a truss. But we made 2 pieces that clearly are not 2-force members. So they're beams. One of them's vertical and one of them's horizontal. I guess we should put labels so we can talk more specifically about which ones we're talking about. So we'll make this A and B, C, D, and E. So A, B, C, and C, D, E are not 2-force members. B, D so far is a 2-force member. Let's put a distributed load just so we have practice working with those things. And let's put some dimensions and units and all that kind of stuff. So let's say that this is 100 pounds per foot for the distributed load, this guy. Let's make this one 300 pounds total concentrated load. Let's make this distance, looks like maybe 4 feet. This one will be 3 feet. And we'll need something here. Let's make this one also, looks like 3 feet. And we need 2 feet to get up to the point where that 300 pounds is, and then another 2 feet if we need it to get up here. All right, so I think that's all that we need for making this into some kind of frame that we can calculate things with. This one, it does have, a lot of times it's good to look for 2-force members. This one does have a 2-force member, member BD. So we can somehow mark that. I don't know, we'll color it green. And then usually the first thing you want to do is you want to go in and figure out any of the external reactions, particularly when it's a frame or frame. Machines, again, a lot of times you can't get the external reactions first. Sometimes even with frames you can't get all of the external reactions. This one we can. There's just a pin and a roller. So that gives us 3 reactions for the point A, or 2 for A and 1 for E. And we have 3 equations, so we can get all these reactions. So let's I will copy this thing and let's just move it down here. Paste. All right. So you may just want to erase the pen and or whatever, or redraw it. I don't know. I'm going to do this here and replace that pen at A with AX, or well, this is AY, and AX. And then E, there was a roller. I want to replace it with EY. So again, I just drew them in the positive X and Y directions. I haven't even really written a coordinate system, but X is normally positive when it goes to the right. Y is normally positive when it goes up. You could elect to choose any direction you wanted to for them. The only constraint is that AX and AY need to be orthogonal to each other. And it would probably help that EY is the same direction as AY, although on EY, you do have to make it perpendicular to the little shelf it's rolling on. So if that shelf was at an angle, you know, some angle like that, then the reaction would have to be perpendicular to that shelf. So that is the constraint on those rollers, is that the reaction should be perpendicular to whatever you're rolling on. And here, the little shelf is horizontal, so I can make the reaction vertical. So now I've got this free body diagram. I could, you know, put in x-axis and y-axis just to have them for sure. And then maybe do summation of moments about A. Well, there's an easier one even. Summation of forces in X equals 0. I have 300 pounds plus AX. Those are the only two in the X direction. So AX has to equal negative 300 pounds. Then maybe I do the moments about A. And I have this distributed load, and I really would rather deal with it as a point load when I'm doing moments. So I will lump it's 100 pounds per foot. It's spread over 7 feet, so it's going to be a total. I'll put it kind of up here. 700 pounds, and it would be 3.5 feet over from this end. I'm just putting it, since it's an evenly distributed load, that means that it's basically functioning like a rectangular area. So I'm putting the 700 pounds, which is 100 pounds per foot times 7 feet. And I'm putting that at the centroid of this rectangle, which would be 3.5 feet to the right of where it started. Just in the center of it, where the centroid would be. So I want to use that 700 pounds to represent the entire distributed load when I'm writing the moment equation. So 700 pounds times 3.5 feet. I've got EY, so I've said that clockwise moments are positive in this equation, so EY is going to create a negative. And it's 7 feet over. And then I've got the 300 pounds, which is going to go clockwise, so positive 300 pounds. It is a total of 5 feet. I didn't put all my little feet symbols on there. All right. Those have to add to 0. So equals 0. So we'll have to solve that. So 700 times 3.5 plus 300 times 5, and then divide that by 7. So EY should be 564. 564.3. And it's positive, so that means that we drew EY, the arrow, in the right direction, which kind of makes sense. EY, the arrow going down, would really not make sense. So then we can do maybe forces in Y or moments about E. Probably simplest to just do summation of forces in Y. We can also use that lumped 700 pounds here. There's no reason to use the distributed load for this. So 700 pounds, actually that's going to be a negative. Let's do a positive first. So AY minus 700 pounds plus EY needs to add to 0. Then we plug in EY as this 564. So basically we do 700 minus the 564 and we get 135.7. pounds. So we've got our reactions. All right. We didn't even say what we were trying to solve in this truss here. You know, what are we trying to look for? If this were a test problem, more than likely you'd be looking for something to do with member BD, which means you don't necessarily need AX, AY, and EY. You could probably get away with one set of them and deal with either member CDE or ABC. We're just solving for everything, though. So at this point, you've got the external reactions, and the next thing you need to do is take the thing apart, pick a free body diagram, ABC or CDE or BD, and draw that. We'll draw all of them, just, we won't need all of them, but we'll draw all of them just so that we have them. So let's do CDE first. So we have that distributed load. Now I'm going to redistribute it instead of having a point load, although we are going to probably do some more equations like moments or forces in X or Y, and you probably do want to re-lump it into the 700 pounds, but for now we'll leave it like this. At C, we have member ABC connected. Neither of those are two force members, so we're just going to have to put CX and CY. At D, that is where member BD is connected. It is a two-force member. It only has 2 pins. There's no external force anywhere outside of those pins on member BD. So we can, instead of writing DX and DY, we can write member B or force BD at this angle, which looks like it's a 45-degree angle based on the geometry. So we can just put, and we don't have to decide is it tension or compression. We can just put one of them. Let's do this, and we'll call it the force in BD. E has the roller was there. We did solve EY is 564, so we can just put that. It is positive, so we know the direction is up the way that we originally drew it. And we can just put 564.3 pounds. So we could stop there, do this free body diagram, and solve for all the unknowns in the truss. But again, let's just draw the others to make sure. Make this 45 degrees. Let's draw BD. D, B. So we know that, or well, we chose a direction for FBD on member CDE, so we have to choose same direction but opposite magnitude here. This one we have to make this piece in equilibrium, so they have to look like that. They could all be wrong or they're all right, one or the other. This looks right, but you don't have to know beforehand. So there's A, B, and C. At B, we have to show the equal and opposite reaction to this thing. So like that. At A, we have AY does point upwards, 135.7 pounds. AX does need to go to the left. I drew it originally to the right, but then I calculated it's a negative 300, so it needs to go to the left. And then I've already chosen CX and CY directions when I drew CDE, so I need the same magnitude, CX and CY, but opposite directions for both of them. So CY needs to go down, and CX needs to go this way. All right. And now I have 3 free body diagrams. BD doesn't actually help me. The reason I draw that one is sometimes it's you can easily make those FBD arrows the wrong direction if you're not careful about how they should be equal and opposite of each other. Maybe you do, maybe you don't. This way it's less likely that you make an error when you actually draw the 2 force member in there, and you can trace how the forces have reactions at each of these points. I would probably use member ABC, probably, just to not have to deal with the distributed load. But again, it doesn't matter. But that's probably what I would do. So we would put A to B. Oh, we did leave off one thing. We left off 300 pounds here. This distance, I don't remember, 3 feet, 2 feet, and another 2 feet, which is kind of getting crowded. Okay. So I would look at that, and if we did forces in Y, we have 2 unknowns, CY and the Y component of BD. If we do forces in X, we have 2 unknowns, CX and the X component of BD. So we need to do a moment equation first. Usually whenever there's 2 unknowns that are at the same point, like at C, CX and CY, that's the best place to do summation of moments. So we will take this vertical free body diagram and do summation of moments about point C. That should give us a value for BD. Let's say clockwise is positive. So CX and CY, they do not create moments about point C. The 300 pounds creates a counterclockwise moment, so we'll make that negative based on the way I chose as positive with 2 feet moment arm. FBD, again, we could try and figure out the perpendicular distance between C and the line of action for BD. Probably not going to do that, just going to go in and do X and Y components of BD, and only the X component does anything about C. The Y component line of action actually passes through point C, so it's only the X component. And the way I've drawn it, it would create a counterclockwise moment, oh no, a clockwise moment, so it'll be positive. So plus FBD. We only want the X component. In this case, since it's 45, they're actually the same magnitude, but the way I drew it, cosine of 45 degrees, that's the X component, and it has a 4-foot moment arm. And then the 300 pounds at A also creates a clockwise moment, so that's plus 300 pounds, and it has a 7-foot moment arm. And then the 135.7 AY, its line of action goes through point C, so it doesn't create a moment at all. So these have to add to 0. And there's only one unknown in there, BD, so we should be able to find the magnitude for that and if we drew it the right way or not. All right, so 300 times 2 is negative 600 plus cosine 45 degrees times 4 is 2.828 times BD, BD, plus 2100, 2100. And those would be foot-pounds. I haven't been writing the units. Should do that. So 2100 minus 600 is a positive number, but it moves to the other side of the equal sign, becomes negative, so I get 2.828 times FBD equals negative 1,500 and foot-pounds, and we divide by feet, and we get FBD is a negative 1,500 divided by 2.828, 530.4 pounds. Now what this does is that means that every time we drew BD, we thought we were drawing it the right way, but we were actually drawing every one of those the wrong way. So remember, BD should be in tension. We drew it in compression, but it's actually in tension the way that the thing is set up. So it means that kind of the loads on it are stretching out, remember, BD. And we do know the magnitude, 530.4, but every time we drew an arrow for BD, we drew it backwards. So anytime we plug it into an equation, we have to remember that we actually did it backwards. All right, we don't know CX and CY. Now would make sense to either do summation of forces in X or Y, so let's do in X. So we have CX, actually we have, the way I drew it here, negative CX plus 300 pounds minus FBD times the cosine of 45 minus 300 pounds has to add to 0. So those are the 4 things that have x components, and then I need to plug in this negative 530 into there. So negative CX plus 300 minus negative 530.4 pounds times only the x component of it minus another 300 pounds equals 0. So this 300 minus 300, those actually cancel out. So it says that CX equals, by the time I get all the signs oriented, it comes out positive. 530.4 pounds times cosine 45 degrees. So CX arrows are the right way, and they should be 375.1 pounds. That's 1. Okay. Then the only thing we're missing then is a value for CY. So if we did summation of forces in y direction, we would have, let's look at it, we'd have negative CY, negative, the way I drew it, negative y component of BD plus this AY 135. So let's write that down. Negative CY minus FBD times the sine of 45 degrees plus 135.7 pounds from AY. Need to add to 0. So I have 3 things in there, and looking at this, there's 1, 2, 3, so that looks right. So now I need to plug in that negative number again for BD. So negative CY minus negative 530.4 pounds times only the y component plus 135.7 at AY needs to add to 0. So this one, I get 530.4 times the sine of 45, which is the same as the cosine. But I add in plus 135.7. So I have a positive number on the left-hand side, move it to the other side, I get negative. CY is also negative, so we drew CY the right way. CY is equal to 510.77 pounds. And it came out positive, which means all the CY arrows are the correct direction also. So, again, on an exam, you would probably be looking for the force in BD and then maybe the change in length in it or something like that, but depending on how easy or hard this frame problem was supposed to be. But this one, that's a reasonable average level problem. Just find the force in BD kind of thing. If it's a harder one, then maybe it's find the change in length in BD, something like that. But you don't have to do all of this work. We could have stopped, right there after we did moments at C and found the force in member BD. All this other stuff is just completing everything, more like a web work problem would do. All right, so this would give us all the free body diagram information for any of these pieces. And what we want to do is we want to start moving into, I talked about change in length in BD because that's the only thing that we really know how to do. We can do stress, axial stress, and we can do changes in length, axial deformation. But these 300-pound and that 700-pound distributed load, they do different things. They do this bending stuff. So we need to figure out how to deal with this bending. So I think I would show you an equation for bending without worrying about where it comes from yet. But we can have, let's call it bending stress. And it can be sigma. Sometimes it does, and sometimes it doesn't have a subscript that denotes it some kind of flexural stress or bending stress. Sometimes this will be called flexural stress. And the equation is going to look like this. Technically, it ends up with a negative sign in front of it. M, Y, sometimes there's a C in there, over I. So it might be my over I or mc over I. Sometimes the negative sign is dropped off, sometimes it's not. But this is the generic form of the equation that is most applicable. And then all the other forms of it are like specific, the maximum stress and things like that. So this is the most general one. So none of the, well, Y, let's start with Y, because that one's the one that we can worry with and get it explained pretty quick. So let's go back to this idea way up here where the cross-section is just a rectangle. So it doesn't matter what the cross-section actually is for how Y is defined, so we'll just use it as a rectangle. Quit doing that. So this is our cross-section of some beam so this might be the member CDE at the top. Maybe that's just a rectangular like 2x4 or something sitting across the top of this frame. ABC could also be that, but it's got a rectangular cross-section. So we know that the centroid for this thing, if it's a rectangle, is just right in the center of the height. So let's put numbers on it to make it easier to talk about. Let's say that this is 6 inches. And we'll put the base on here of 3 inches just to have it. We won't need it though. All right. So if I know that, got this 3 by 6 inch rectangular block of whatever this material is, and I've laid it across the top of this frame and put that distributed load on it and set it on the little shelf and all that kind of stuff. Then I know that this rectangle, the centroid is 3 inches from the bottom, right there. And I know that that line, the dotted green line, is the thing I've called the neutral axis. And when I want to put a value in the equation here, if I go back to this picture, maximum stress is on the very top and bottom of the beam. So on one side of the beam is maximum compression, and the opposite side of that is maximum tension. And then the closer I get to the neutral axis, that centroid of the cross-section, it goes to 0, no stress, no flexural stress anyway. There's different kind of stress there, but not flexural stress. All right, so if I look at the equation here, sigma equals my over I, y is in the numerator. Y is the distance from the neutral axis. Y equals distance from the neutral axis to, and I'm going to call it the point of interest. On the beam's cross-section, or of the beam's cross-section. So sometimes you want to know what the stress is at some specific point across the beam. Most of the time, the point of interest is where the maximum stress is, which is either the top or the bottom of the beam. So for this rectangular beam, I would put a value for, if I want to find the maximum stress. This beam, it looks like there's some parts of it that are clearly loaded in a way that makes the tension on the bottom, compression on the top. Point D actually pushes back up though, so maybe there's some little part in there where it might actually have tension on the top. That's stuff that we'll figure out another day. For now, let's just say that I want to think that maximum stress is either at the top or the bottom. So sigma max is either here in tension and in compression on the bottom, or the opposite of that. There's either maximum tensile on the top and compression on the bottom, or compression on the top and tension on the bottom. Most of the time it's compression on the top and tension on the bottom. Either way, y is the distance measured from the neutral axis either down to or up to some point of interest, whatever this point of interest is, which is usually the top of the beam or the bottom of the beam. So I would put in either 3 inches or negative 3 inches, depending on if I wanted to measure to the top of the beam or the bottom of the beam. So for this little beam, y equals 3 inches to calculate stress on the top of the beam. And y equals negative 3 inches to do the same thing, calculate stress, but on the bottom of the beam. Calculate. All right. And you can make it any number in between. If I put y equals 0, that calculates the stress right on the neutral axis. If I put a y in the numerator of that equation, I get stress is 0, which is what it's supposed to be at the neutral axis. Flexural stress would be 0 at the neutral axis. And so I can put any number between 3 and negative 3 into this equation for y. And the number I put determines where exactly am I calculating the stress on this cross section. Most of the time, I either want the top or the bottom of the beam. M and I are not as obvious. So let's talk about I first. I is called the moment of inertia. And it is, if I had to define it to be something, I would say it's the beam's resistance to bending. So obviously the bigger number I put in for I, the smaller the stress gets. And so a beam that has a really large moment of inertia doesn't bend a lot, doesn't have as much stress under it, and that kind of thing, because I've put a really big number in the moment of inertia denominator of this equation. It's based on the cross section. And so it kind of, the more material this beam has away from the neutral axis, the larger the moment of inertia gets. And so that's why you might, a lot of times, see this I-beam shape. So what they're doing here is they're taking, all this material and moving it away from the neutral axis. Neutral axis would be right through the center of this thing. And so the I-beam says that, hey, to maximize this idea of moment of inertia, I'm going to move as much material as I can away from the neutral axis, get a large moment of inertia, and maybe save some material, versus just building, an equivalent solid rectangle that would have a higher moment of inertia than here, but it's not, it doesn't scale. So the moment of inertia for this rectangle, the same size as the outer part of this I-beam, is not significantly different compared to the amount of material you're using to make this solid rectangular piece. I mean, that an I-beam that's or converted over to a rectangle would just be this massive beam. And you could get almost the same performance out of the I-beam, which doesn't have all of this material in here. All of that's missing, but it has almost the same performance as that solid piece of rectangular steel or whatever it is you made the thing out of. And we'll calculate moments of inertia specifically, sort of like calculating a centroid, but they have their own equations. In fact, remember the centroid equation had this idea of first moment of area. Well, moment of inertia has second moment of area. So instead of the integral of y dA, integral of y squared dA. So the second part is the squared in there. And so we're not going to ever need to integrate them. There are charts similar to the centroid charts that are going to give us these moments of inertia, second moment of area, whatever they might be labeled. But that's where we're going to deal with those. Also, there are a lot of standard beams like I-beams and T-beams and C-beams and right angle beams and all this kind of stuff that the moment of inertia is pre-calculated. So there's charts and charts and charts of these moments of inertia that we can just look up. That's how we'll start, so that we don't have to worry about how to get the moment of inertia. We'll just look it up in the correct chart. So that only leaves M. So M. And the negative sign, again, the negative sign, if you want to know why it's in there, the reason it's in there is to make tension stresses, bending stresses, come out as positive. Because think about this beam right here, tension's on the bottom. So that meant I had to put a negative y distance in this rectangle. You know, I had to measure, to calculate this number, y had to be this one, which is a negative whatever half the height of the beam is. And so if I put a negative y in there in this equation, without that negative sign in front of it, the tension would come out as a compressive number or a negative number. And we don't want that. We want our tensile numbers to be positive and our compressive numbers to be negative. So that negative sign flips the sign on the whole term, so that you have tension coming out as positive terms and compression coming out as negative terms. So that's why the negative sign's in there. But we need M. And M is, yeah, we'll spend a little bit of time dealing with M. So M is called the bending moment. This diagram isn't actually in equilibrium. You know, what's going on these surfaces over here and over here, what's going on over there, we didn't actually draw those forces. So we need to maybe draw a better free body diagram of a beam section and see where this bending moment's coming from. So let's take again a little simply supported beam. And let's just put a point load in the middle of it, enough so that, you know, it would bend downwards. And then think about a free body diagram of a piece right there. Now this one I'm not going to draw so curved. Obviously it does curve if it bends, but that radius of curvature is usually pretty small for real pieces. You know, if it's a machine or a structure, then you don't want to design it in a way where there's a whole lot of flex in these parts. But there is some. So I'm going to draw this little piece not curved. It's certainly not curved like the one I drew earlier. So I'm just going to draw it as a little piece of a beam. All right, so this is the little piece that we circled there, just blown up bigger. And so that means that we kind of chopped it off here and here. You know, somehow we cut that open so we can see internal stresses and, well, and internal forces. And what's going on here, there are some forces that are, if I pushed hard enough straight down and the beam was a material that it just sheared, so like cutting it with scissors, then there's some amount of force that's just trying to shear this beam. You know, there's just a shear force. I have to, if I put one way, then I have to put the other one the other way because I don't want it to actually shear. So I have to make these balance, right? And these can be shear force V. But so these two shear forces balance one another so that this little piece, since I cut both ends of it off, then there's no reactions anywhere. This is the pin, you know, I'm not looking at the pin, I'm not looking at the roller. So these two forces have to balance one another so that summation of forces in the y direction add to 0. So summation of forces in the y direction have to add to 0 for this free body diagram. Otherwise, this little section, this little chunk of the beam has broken, you know, it's kind of cut itself out of my beam. You know, it's moving up or down relative to the beam not moving up or down. So this just says that V, the way I drew it, V shear force minus V equals 0. So that works out. We're balanced in the y direction. Now I do have you know, I do have some potential point load up here. We'll call it P for a point load. So there is that. So basically these have to equal P, right? The shear forces have to balance one another. And so the directions I'm not worried about right now. And I don't always exist, you know, I could have, might have made it a little clearer if maybe the section was over here. So I'm not under that point load. So this thing's not something we're worried about right now. That part's not super important for what we're doing. We just need to know that there's shear forces that want to chop this little section out, and they need to balance one another. But when they balance one another and there's some distance between them, so there's some, we'll just call it X. We'll redraw this thing probably tomorrow a little clearer, so it doesn't matter. But there has to be some distance between, not tomorrow, Wednesday, between these two things, and they create what's called a force couple. So basically they're forces that are separated from one another, and they make this little piece now want to spin around in circles, right? Because it looks like the way I've drawn these to make them balance, it's going to want to spin around clockwise, and I don't want it to do that either. So there are actually these forces. And when I draw that one, I probably need one over here also. And I don't know, sometimes these could be 0, sometimes, M could be 0, V could be one thing or the other. Technically, they may not be equal to each other, right? Because I could have that point load, so I could be a little more specific and say that this is the shear force on the left-hand side, and this is the one on the right-hand side, and this is the moment on the right-hand side, and the moment on the left-hand side, so because they may not be equal to one another. But I just know that I need to be able to balance this stuff out. And these curved arrows, we haven't used that a whole lot, or maybe not at all, but these things are concentrated moments when you draw a curved arrow like that. And in our specific case, when it's in a beam, that's what we're calling the bending moment. And that bending moment, whatever the value of that M is what we put into that little equation, sigma equals M, the bending moment times Y over I. All right. Let's do one of these and actually calculate flexural stress. So let's make a really simple beam. Oh, right there. Okay. Yeah, go ahead. I drew one, and then I drew the other one the opposite. And yeah, because that part of it I don't want to get too much into until tomorrow or to Wednesday, the next lecture. For now, let's just assume those are the correct orientations for all the arrows. There are reasons why I want one going clockwise and one going counterclockwise on certain ends of the beam. But for now, let's just assume it's kind of like X goes to the right and it's positive and Y goes up and it's positive. Let's assume it's that kind of thing for right now. Right now, I'm just trying to make a little free body diagram that I could potentially say is an equilibrium, static equilibrium. So ML equals MR, and they're going opposite directions. VL equals VR, and they're going opposite directions. They may not actually be the same thing. There might be other things going on. But for now, let's leave it like that for now. Actually, this next thing might help it make some sense because we're going to put numbers on it. Let's just do a pretty simple one. We've been drawing this beam that has a pin and a roller, so let's just keep with that. Remember, this is simply supported, but let's put numbers on it. And let's say that this is 3 kips, so 3,000 pounds. And let's make this 4 feet. And I don't want it to be centered, so let's make this 3 feet, even though it doesn't look like that. Just so it's not centered. Sometimes people have problems with stuff being centered. So let's assume that this is our beam, and we want to calculate the flexural stress in the beam. Now, we don't necessarily currently know how to calculate the maximum flexural stress in the beam, but let's just say that we have a reason that we want to calculate the flexural stress right here. And let's say that X equals 3 feet. It could be a variable, just x, and we could put any number in there. But let's say x equals 3 feet. So there's some reason that we want to know how much flexural stress is in the beam 3 feet from the pin. And the beam is 7 foot long, and it's got 3,000 pounds on it. We need to know what kind of beam this is because I is in the flexural stress equation, and I is determined by the shape of the beam. So we need to come up with some kind of beam. For now, I said that we were going to use this idea of the some beams are already pre-calculated for us. And I have in general resources over here, somewhere, reference materials. There are a couple of the charts. I don't think they're all of them, but there's a couple of charts, C sections, S sections, W sections, WT sections. So let's use W. And let's open that. So this is a table. W is actually I-beams, but it's W is because it's a wide flanged I-beam. The flange is the top and bottom part, the way the picture's drawn here anyway, like that. So the flanges are those horizontal pieces. The vertical piece is called the web. In this chart, you've got all these numbers. Like you've got numbers for area, depth is what they're calling basically what you might think of as the height of the beam from top to bottom. The flange, you have two things. You have the width of the flange. These W's are wide flanged I-beams. You've got the thickness, so that's how thick, is the flange itself. So can I draw on here? Oh, wow, I can draw really big. Well, I'd like to draw a smaller line. There we go. That is the thickness of the flange. This part is the flange. So is this part. They should be identical on a I-beam. What else is in here? The web thickness would be this guy. And then I've got two sets of columns, one that says axis XX, one that says axis YY. And then on this picture, there's an XX axis and a YY axis. So the difference here is that you could normally, you would load this I-beam with loads on the top of it. So, if this thing is a I-beam, it would kind of look sort of like this, right? And I would put loads on the top of it. And that's the normal orientation. And so if you do that, if your loads are perpendicular to what they've labeled as XX, you use all of the axis XX numbers here. Sometimes you have side loads on the beams, or maybe you put the beam in sideways for some particular reason. But sometimes you load, you load the beam with loads that are going this way, perpendicular to YY. In that case, you use these three at the far right that are under the axis YY columns. Those are not the normal orientation for loading the beam. So unless you're specifically told that this beam is loaded on its side, or it's drawn sideways with loads on the side of it or whatever, then you're not going to use the axis YY set of stuff. You're going to use the XX because that's the normal orientation for these beams. And under there, they've got three things. They've got S, which we're not going to use yet. They've got R, which we're not going to use at all in this course. And there's that I. So that I is the moment of inertia, and it's the denominator of our flexural stress equation. And look at the difference here. So when I load the beam the right way, I put a 15,000 inches to the fourth in the denominator. When I load it sideways, I put 940 inches to the fourth in the denominator. So the beam is, 16 times stronger oriented the right way than it is on the side. There might be, there are going to be reasons to attach things to the side of beams, but we're not dealing with that right now. So that beam, let's look at this name of it. These are the beam designations. Those are the names. And there's three parts. You've got the name, which is, or the type of beam. Most of them make a lot of sense, like C's look like the letter C, capital letter C. T looks like a capital T. I is in our charts, the one that we have are W's. So they're actually wide flanged I-beams. And they give you a picture, so you should be able to see what the thing looks like. But the W is wide flanged I-beam. The first number, in this case the 36, this is the nominal, so like not exact but kind of average depth. And again, depth is, they're calling this distance depth. So this beam is almost, and you have to look at the bottom of the page to see the units, depth in inches. So this beam is like 36 inches tall. So this is a big beam, 3 foot tall I-beam. This last number is the weight per some kind of unit length. And again, you have to look at the bottom to see what the unit length is. Pounds per foot. So for every foot of beam that I chop off, like, you know, that way, 1 foot, that section of beam, that 1 foot long section of beam weighs 230 pounds for this top one up here. And in general, the biggest beams are at the top of these charts and the smallest ones are at the bottom. So this bottom one is still an I-beam, it's still W. It's 4 inches tall and weighs 13 pounds if I chop off a 1 foot section of it. And its moment of inertia is way smaller. You know, its moment of inertia is this number, 11.3. The moment of inertia for that 230 pound beam was 15,000. So let's use one of these smaller ones. Let's just pick something, I don't know, 8 by 40. So we'll use this row of stuff. Now, I said that the nominal depth was listed in the name. The actual depth is the one that you need to use when you're calculating Y or something like that. So we need the actual depth of this W8 is 8 1/4, and its moment of inertia is 146. The units at the top of this column are inches to the 4th. And these 8 1/4 is inches. So we can take that information and go back to our little beam over here, right here, and we can say that this thing is a W8 by 40, and it has depth equals 8.25 inches, and I forgot it, 146. Wow. All right, so now we just need, we can get Y from the depth, and we just need M. So here's how we're going to do M. First, we need to get the external reactions. So we need, let's draw it down here. $3,000 pounds. There's some, we'll just call it BY, I didn't even label them. And then AY. AX is going to be 0 because there's no other forces in the X direction to, no other external forces in the X direction. So we can do, let's do moments about B. So summation of moments about B equals 0. We'll do clockwise positive. That'll give us AY times 7 feet minus 3 kips times 3 feet. Must add to 0. Therefore, AY is some number. 3,000 times 3 divided by 7. 1285.7 pounds. And we can figure out BY if we also needed that. We're not going to need it though. So let's plug that number in for AY, 1285.7 pounds. And then what we're going to do here to figure out this bending moment is inside the beam. So it's kind of like the internal force when we're doing axial stress, except it's an internal bending moment. So to find internal forces and bending moments, you have to cut the beam open I'm interested at this point 3 feet from the end, so I'm going to cut it right here, 3 feet, and draw that free body diagram. And I could also draw the right-hand side, but then I need to know what BY is, and so I'd have to go figure that out. I'm just going to draw the left. I'm going to draw this little piece. I'll draw it a little bigger. All right. So on this piece, I have AY, which is 1285.7 pounds. Nothing else, right? There's no other external forces on this piece, so that I know can't work because that piece would be spinning and accelerating all over the place. So I have to go back here and use this set. You know, I cut the right-hand side. I'm looking at the right-hand side of a little piece of this beam, and I said on those sides, the shear force goes down and the bending moment goes counterclockwise. So I'll just put that there must be some shear force, V, and some bending moment, M. Now, this thing might be in equilibrium. At least it has a chance to be in equilibrium, depending on what I put in for V and M. And I can put in that, well, if I do for this piece, summation of forces in the y direction equals 0. I'm going to use my normal x and y. So 1,285.7 pounds goes up at A, minus V has to equal 0. Therefore, V must equal 1,285.7 pounds. We're not going to do too much calculation with this V, or maybe not any calculations, but this shear force does have the potential, if that number is really big and the cross-section of this beam is small enough, it could just shear it like you're cutting it with scissors or whatever. We're assuming that 12,000 pounds of direct shear is not too much. There is also a different shear that we're not going to look at in this course, but if you're mechanical or civil and you take continuation courses, there is a shear that's not even shown on here that could also affect things. We're more interested in this M. So what I would do to calculate M is do a moment somewhere, because that's where it's going to show up. So I'm going to do summation of moments, and I'm going to do them about this cut surface, just so I don't have to deal with the shear force. I'll say that, let's say that counterclockwise are positive, since I drew M counterclockwise. They still need to add to 0. So far, the shear force keeps the beam from moving up and down, that little section of the beam moving up and down. We got that in balance, but the combination of the way that shear force is and that 1285 reaction at A would make this little section of beam spin around clockwise. So this bending moment is stopping it from doing that. So I've got, I didn't put it on here, but remember we were interested in it when this distance was 3 feet. That was part of the original problem, is that we wanted to know something about the flexural stress 3 feet in. So we've got a dimension there. So if I do this, I have going clockwise, so negative 1285.7, this is AY, times 3 feet, creates 1 moment. So that's, this moment this way. All right. M, I don't think we've used a concentrated moment. So how you put them into moment equations is you just put plus or minus M, or whatever the magnitude is. In this case, we don't know the magnitude. So I drew this one counterclockwise. I said that counterclockwise moments are positive, so I just put plus M. There's no moment arm associated with a concentrated moment. It's already built in there. And so this just says that, well, M equals, it's going to come out positive, 1285.7 times 3, 3857.1, and the units would be foot-pounds. Okay. So now we've got M. We've got somewhere up here, we looked in the chart and got a value for I, and we kind of have Y. We haven't really gotten it yet. We have the depth of the beam. So let's draw a little cross section just to make sure we have the right value for I in there. So this is an I beam. So it's something like that. And we know that this distance is 8.25 inches. We got that from the chart because this was a W8 by 40. So we know, now some beams like T-shapes where the neutral axis is not obvious, that is also listed in the chart. But for an I-beam, the neutral axis is right in the center. So there's the neutral axis. So for Y, I want to put in the maximum distance I can. So in this case, it's either measure from the neutral axis up to the top of the beam and put in 4.125, or measure from the neutral axis down to the bottom of the beam and put in negative 4.125 inches. So the only difference is, do I want to calculate a tensile stress or a compressive stress? You know, the top of the beam or the bottom of the beam. And the way this beam is loaded, I can just tell, look at it and tell that tension is on the bottom, compression's on the top. So let's say we want the maximum tensile force. Since the 4.125 is the same either way, it's just positive or negative, I want to use the bottom, which is actually the negative y. All right, so here's my equation. Sigma equals negative m times y over I. So negative m is 3,857.1. Those units are foot-pounds. I want to do the bottom of the beam to get the tensile force, so that's a negative 4.125 inches. Now I've got unit problems here. I've got foot-pounds times inches, so I've got to convert something. I probably want to get rid of the feet, so that sigma comes out in pounds per square inch. So probably want to get rid of the feet. So let's do 12 inches per foot so that we can cancel those out and have inch pounds in the numerator. And then we'll divide by, I think it was 146. I is 146 inches to the fourth. So this will give me pounds per square inch, which is PSI, which is a stress unit, so that makes sense. And it gives me a positive number because I have negative 3,800 and negative 4. So I get a positive number, which would be tension. And let's see what I get. 38 times 4.125 times 12 divided by 146. I get 1307.7 units of PSI. 1,300.707. And then that number I can compare to, usually this is a tensile number, so compared to tensile strength of the beam's material. These beams are usually some kind of steel, and the yielding tensile strength of steel is in the 30,000s or so. So we're nowhere near causing this thing to yield. You know, we've got a factor of safety of I don't know, 15 or something. I don't know, a lot, more than one. So we're safe. That's the general idea of what we're going to do. We're going to expand on this because it'd be way more interesting to take this same type of problem and figure out, okay, what is the maximum in anywhere in the beam? Because if I put x as some other number, x is 2 feet or x is 4 feet or x is 7 feet or whatever, then this little free body diagram, suddenly the moment changes because I used that 3 feet to calculate that moment. So that bending moment can change from one end of the beam to the other end of the beam, and I need to know where's the worst case. You know, where's the bending moment, M maximum? What number is the maximum value I can put in for I or for Y? Actually, I should not change. The cross section of the beam shouldn't change from one end to the other, so I should be constant. But M and Y might change depending on what I'm looking at. So that's what we're going to do next time, is how do we figure out where the maximum bending moment is. So there's ways to do that. But I think for now, we have enough information. Also, if you didn't finish, I think it's homework 8 and 11, they were due on Friday. I think I opened them up until Wednesday, Tuesday or Wednesday or something. So you got a few more days to work on those if the test kind of took precedence over finishing those things.